Thank you, Sandia. It's difficult to follow this. Thank you to the ACM and the IEEE Computer Society. I'm just deeply honored for many reasons, but in a special way because I have so many dear friends in this community. You've always been so welcoming to me. Always coming to ISCA felt like going back home. And I truly hope we can all be all together again soon. My talk today comes from a particular perspective that I want to explain first, and that is the perspective of a practitioner. See, my father was a surgeon who was always investigating new treatments and collecting case studies. He was participating as well as publishing in medical conferences his entire life, despite the fact that he actually never held an academic or research position. He was dedicated to the practice of medicine, but he always made time to advance the knowledge in his area, which is something that always struck me. And I don't know if consciously or not, but in some ways I followed his footsteps and became a practitioner of our discipline. I think this award in some ways reinforces the place for the practitioner in the computer architecture research community. Practitioners, in my view, they complement the array of voices we have in research by being in a position to publish in the past tense, in that they have the benefit of publishing about systems that were built and deployed and used, so they can bring a perspective about from the usage of those products and retrospectively help us understand what worked and what did not work. I think that's an important voice that I'm delighted to see that ISCA and the architecture community continues to make space for. Now, this is an award about the practice of warehouse scale computing, so I thought I'll just give you a brief first-person perspective of how I saw that come about. As you can imagine, the quote that good artists copy and great artists steal is appropriate here. There's a lot of stealing going on. I think we could go back further, I suppose, in the history of warehouse scale computing. But to me, the first milestone really was VAX clusters. Even though there had been distributed systems and clusters before, VAX clusters in the 80s was the first system, distributed system that was a commercial distributed system that actually attempted to provide a single system image at the time, which, you know, for those of us who remember, was a very hard thing to do for a distributed system, make it usable as a single unit. So in my view, that's really where that starts. This is one of the seminal papers in this area. In the 90s, things began to pick up pace. People began to look at the powerful microprocessors being built at the time and trying to figure out maybe we can have alternative to traditional supercomputers and put together these low-end systems into really powerful machines. There are many examples there, but to me, the most notable are the Beowulf clusters in NASA. I believe that's Thomas Sterling over there in front of one of the first ones. And you see on the right-hand side, the logo for the Berkeley now Networks of Workstations project, led by Thomas Anderson, David Culler, Dave Patterson, Eric Brewer, many others participated on these. So this certainly is part of the DNA for what were to become warehouse scale computers. Now, by the time I arrived at Google, I found a company of programmers who were short on cash, but really not short of confidence at all. And they were already building their own machines at the time. As you can see here, this happens to be in the Computer Museum. Not particularly elegant, I suppose, might be one way to say it. You can see how interestingly the boards bulge in the middle through the weight of the disk drivers who happen to be sitting on top of the DRAM, and the careful placement of cork between the PCBs and the sheet metal to provide some defense from some short circuiting. Now, I didn't come to Google to work on any of that. The Piranha project Sandia mentioned just a while ago had just been canceled at Digital and Compact a few months before tape out. And that drove me to try to become a software engineer. This hardware engineer seemed hard. And I came to Google to become a programmer, risking abandoning the field of computer architecture altogether. As it turns out, learning software engineering is actually not a really bad move if you are to understand how to design the software-hardware interface, being one of the definitions we have of computer architecture. So things had a way of working out. At Google, I was at the right place at the right time. After being a programmer for a couple of years, Urs Hutzler wanted to start an effort to build a team that would grow to become the platforms team, the team that would define what the modern data center would become. Now, in the company of programmers, I was probably the only person with a hardware pedigree, so I was maybe not the natural choice, I was the only choice. And then I became involved with this area, the hardware area at Google. What you see here is the first rack that I actually, that was built by the team that I was leading. It's colored because it was a commemorative one. It was the 1000th rack that Google had built at the time and had signatures of lots of people there. Now, at that time, you have to remember, this is the time of colo facilities. These are third-party hosting business. Those are the data centers. At the time, they looked a little bit like this, and Google ran on those businesses as well. The thing about it is that they were designed by a collection of engineering teams that really knew very little of each other's disciplines. So the civil engineers would put up the building shells. Mechanical engineers figured out how to provision cooling. Electrical engineers would deal with power conversion and distributions and UPSs, et cetera. And then hardware designers would build servers and software engineers would write internet services. None of those folks really ever cared to talk to each other very much. So it was not really a surprise that the overall quality and efficiency of these systems back then was rather terrible. So we had a low bar to go over to begin with when we began to think about designing data centers as an entire unit. And we started actually with this idea of compute containers, you might remember. We were infatuated with this idea. We were going to deploy very quickly these prefabricated computing units with thousands of servers in them inside shipping containers. And that would allow us to do all sorts of things in terms of controlling airflow and the economics of prefabrication, et cetera. What you see here is a literal tabletop exercise actually happening back around 2004 when they're trying to figure out how to put containers together. The next photo is our first prototype of a compute container secretly being loaded into Building 40 at Googleplex in Mountain View just shortly after. I'll give you a view from the container from the inside. One of these three is me. I won't tell you who. It might be hard at this stage. But the other ones will be in this photo are Will Whitted and Bill Hamburgen, who are our lead industrial mechanical engineers on that design. Now, the cool thing about this container experiment, it was that for the first time, we actually could design the whole thing together. We designed the entire building. The building was the computer. So we could optimize cooling knowing exactly what the heat loads looked like. We could design the servers knowing what the software that was going to exercise those servers actually looked like. We could optimize power conversion from the electrical substation all the way to the chip level. And that allowed us to get huge improvements in overall energy efficiency. And then finally, we could design software that could tolerate less reliable hardware and allowed us to source actually lower end parts, as well as making maintenance more efficient because you could batch maintenance when things fix as opposed to having to run to fix them. Now, over time, we realized that although we were really infatuated with this idea of containers, they really weren't necessary. We could get all the benefits of the controlled airflow and ease of deployment and prefabrication the containers got us on something that looked more like a large data center floor. And this is here to just to give you an idea of what a modern data center looks like, or a warehouse scale computer looks like. It's difficult to convey with photos the scale of these things. It really, I mean, I remember, you know, having designed some of these myself, and still the time that I went to first visit them, it was still a moment of awe for us. A little bit more of a visual, these are cooling towers who are nicely lit by, you know, Google's color spotlights in one of our facilities. So this is the external mechanical cooling systems. This gives you an idea of just the size of the mechanical plant that is necessary to keep these massive computers from overheating. And then just finally for scale, it's remarkable that this is a computer that in order to fit it in the frame, you have to photograph it from a helicopter. And that's again, a picture of one of our facilities. Now, I want to switch gears a little bit and talk about the subject I know a bit better than warehouse scale computers, which is of course myself. This is one of these situations where I think you're allowed to indulge just a little bit in this. I knew I wanted to be an electrical engineer since I was 8 years old, and I was helping my grandfather at the time work on his ham radios. Now, don't get me wrong, that's a really dumb idea, right? 8-year-olds should not be making career decisions. I really discourage you from asking your children to do the same. But there you go. I was never really a child prodigy. In fact, if anything, I was more of a late starter. I frankly struggled a bit during my PhD, but my luck actually was about to change in large part because of the thing that really matters in life, which is people. Nearly, 25 years ago, I got a call from Norm Jopi on a Saturday in my grad student office at USC, inviting me to interview at DEC Western Research Lab. Now, this is the Norm Jopi, right, winner of this award 5 years ago, who back then was already a superstar in our field. I mean, the fact that he knew who I was just blew my mind. And I don't think anything in my career since then has compared to the feeling I had that day. It definitely went to my head. Maybe the only one that compares is when Sandhya called me a few weeks ago to let me know about this award. Although there is a close second moment to these two, which is being asked by John Hennessy and Dave Patterson to write the foreword for the 5th edition of their famous book, Computer Architecture, A Quantitative Approach, a book that the first edition came out when I was entering grad school. So that one came close. I joined DEC World, and I had the chance to work with people like, you know, Kurosh Garacholo, a close friend and a colleague at Google still today, and then collaborate with a number of people in the academic community at large. Folks like Susan Eggers and Sarita Adve, Matteo, Giuseppe, Laurie Bappé. Mark Hill wasn't a collaborator at the time, but I met him at that time, and over the years, Mark has been both a friend and a mentor to me in this field. At Google, I had a chance also to collaborate with folks like Tom Wenish and Christos Kozirakis. All of them have been people that, you know, helped shape what this field was to become. Now, perhaps nothing summarizes the impact that friends and fortune, I guess, can have in your life, and the story of how I came to join Google. I was convinced by Jeff Dean, who had been my colleague at DEC, who asked me whether the other company I was considered had ever served me creme brulee during my interviews. It turns out he was right. Google was the only one who had served me creme brulee. And Jeff knew me well. He knew creme brulee was my favorite dessert. So he made sure that there was creme brulee available every time I came to Google. So that was it. That sealed the deal. Now, at Google, it's difficult to come up with a short number of people that have contributed to this. But the brilliance and generosity of folks in the platforms team at large really are essential to the work that's behind this award. I'll just mention a few names here. Wolf Weber was a co-author of some of the early papers on warehouse scale computer with me, also with Eduardo Pinheiro and Jiao Bofan. Urs Hutzler has been a close colleague for many years and probably the single person most responsible for the overall technical successes of Google at large. Bart Sano, he managed the platforms team for the majority of its existence, and I was the tech lead for the team that Bart managed at the time. So he's responsible for really implementing this as well. And then, of course, Partha Ranganathan, who is our technical lead today and is taking Google's architectural innovation to the future. Speaking of people, this is the part where I really feel like I can brag. I would put my list of student interns against any of you. I've been incredibly fortunate. These are folks that are very accomplished in their own rights. They are distinguished engineers at Google. They are founders of companies. It's just a remarkable lineup that I had the privilege to work with. Finally, there's my family. Although my dad's no longer with us, I am so fortunate to count with the love and support of my whole family. My mom, Cecilia, my godmother, Margarida, my uncle, Alberto, and his family, my siblings, Paula, Tina, and Carlos, and their families, and my wife, Catherine Warner, who is, this award that life gives me every day. I'm very grateful to all of them. I'd like to close my talk just mentioning 3 things that I've learned, let's say, in this first half of my career that might be useful, perhaps, for some of you who are starting right now. The first one is just realize that, especially those of you who are computer architects, you stand on a foundation of knowledge that really enables you to do lots of different kinds of work. So don't pigeonhole yourself. I, for one, really never let my complete ignorance on the topic from stopping me from giving it a go. As you can see in part from this list here, I went from chip design to writing production software to fiddling with things like imagery satellites and launching them into space, building digital maps, looking at computer security, and more recently working on technologies to fight the COVID-19 pandemic. I recognize this is risky, but the rewards are incredible. It's made for a really rich set of professional experiences. I encourage you to attempt career suicide every once in a while. You might be surprised, you might fail at that. Lesson number 2, I think Sandhya mentioned something to the fact that I try to sort of communicate clearly some simple concept. This is something that I've done actively, in that I always felt that the problems that are most worth solving were really obvious problems, really easy for you to explain it to anybody. And if you're working on problems, you have the difficult time explaining to people in a short sentence, why is it that it matters? There's a chance, it may not always be the case, but there's a chance it may not be important enough. I'm going to give you an example of, my journey in the deep appreciation for the obvious over the years, which has been a line through my career, through some of the papers we wrote. This is ISCA 1998, a paper with Ed Bugnon and Kurosh Karachola. It's a long paper, but there's a short summary. And here you go. High-end microprocessors are being sold to commercial workloads. So why are we designing them for number crunching? That's what the paper is about. Pretty straightforward. That's what we try to attack with that. Another example, the Piranha effort Sandhya mentioned a little earlier. A long title with many of my collaborators at Digital. Now, this is what this paper is really about. TLP is easy, ILP is hard. Perhaps we should go for more simpler cores on a single die. That's it. You don't need to read the paper. That's what it is about. Now, the attack of the killer microseconds with Mike Marty, Dave Patterson, and Partha is a more recent work. Again, pretty obvious problem, almost embarrassing to mention. These days, most of the interesting data center-wide events run at latencies that are at the order of magnitude of microseconds. When we look at the hardware and software we have today, they do great at milliseconds, they do great at nanoseconds, they are a disgrace at the microsecond. So that's a problem we need to solve if workloads running these data centers are to be more effective. The tale at scale with Jeff Dean, here's the summary. Large-scale services should be resilient to performance hiccups in any of their subcomponents, right? If you built a large-scale system that if any piece of it slowing down slows down the whole thing, that wouldn't be good, right? Because the likelihood of subcomponents slowing down in large-scale systems gets higher and higher. And now here's the award for obviousness in computer science. This is the paper with Urs Hustler, which I frankly was reluctant to publish for at least a couple of years, fearing that it would come across as condescending to the computer systems area. And as it turns out, it's my most cited paper to date. And this is what this paper is about. Right? So I hope you agree with me that it's, there is a way to understand whether you're working on really big and important problems. And one of those ways is to understand whether there's an obvious problem staring you in the face. Don't let go of that problem. Keep working on it. My final lesson for you all is the importance of, over time, learning to get an emotional detachment from things that you've done before that arguably have been the foundation of your success. You need to create some separation there. I'm going to give you just this one example. You know, at Google, I think we're largely successful on a strategy based on not building chips ourselves. You know, I was a bit traumatized by my chip design project having been canceled before I came to Google. So as a tech lead for this area, I focus on trying to influence microprocessors and other chip designers to build the chips that were most useful for us, and then we'd assemble them into the best and most efficient systems we could. And that strategy paid off incredibly well and is in fact probably behind the success of warehouse scale computing in its early years. But then around 2012 or so, machine learning began to actually really work at scale. And for the first time in my career, there was a possibility of building a specialized computing engine that could have broad applicability because so many things can be solved with machine learning. So that was a time where we had to throw away our previous philosophy for system design at Google. I had to throw away my philosophy for system design to Google and realize it was time for us to build silicon. And Bart Sando, Jeff Dean, and myself started a program that was to become the Google Tensor Processing Unit, which is special for me for yet another reason. It's a time where things have come full circle. This was a time where I had a chance to call Norm Jopi and finally convince him to join Google. Norm was then going to become the leader of this effort, the chief architect for a Tensor Processing Unit. And he is there with Google today, which is really special to me. Now, in conclusion, I think it's interesting to observe the world we are living in right now in many ways, but in one particular way is by noticing how, you know, maybe in normal times, computing and information technology has become so essential to society for the last few decades that it's actually become a little invisible. It's easy to underappreciate the impact that our field has in the world at large. Now, as we are very far from being in normal times, I think the contributions of disciplines such as ours here to the welfare of society now are really in clear focus. And that is very inspiring to me. It inspires me to continue to work in this field. And I hope it inspires all of you as well. And with that, I'd like to thank you all very much. And I'll be delighted to answer any questions you might have. Thank you again. I'm deeply honored by this award.
Thank you, Luiz. That was inspiring indeed. For folks in the audience, please use the Q&A for questions. I will wait on those. But in the meanwhile, I have a couple of questions for you, one from Giuseppe. Luck cannot be the reason to succeed at Google, Giuseppe says. So what was your professional strategy?
Don't underestimate luck, but I get the spirit of the question. I think the most important thing was to look for bigger problems. To begin with, frankly, I was desperately trying to learn how to be a programmer. I mean, I could program, as many computer architects. I had worked on very large C++ architecture simulators. But there's a difference between doing that and writing production code. I very quickly found out some of the best people that could teach me. And of course, Jeff Dean was there already, but maybe more than anybody else. Sanjay Gemawat is the best programmer I have ever seen. And I had the privilege of, sharing the keyboard with him and programming together with him over the years. So I just looked for clever people. And they, by and large, have been sort of generous with their time, and they help me move forward. Urs Hustler is another example of that. I learned a ton from him. There's so many others. I mean, realizing that you need help and you can benefit from the expertise of others, especially when you enter a new field, something I've done a few times in my career, it's super helpful.
So, Giuseppe, I still see you have your hand raised. Is there something you specifically wanted to add to this? Okay. So I will ask a question with respect to things. As you know, warehouse scale computing is now something that a large section of the research community is actually trying to contribute to it. And so a question arose in yesterday's panel that I thought might be good for you to share your wisdom and experience on. And that is that as an academic, it's really hard to conduct experiments at scale. And for those with limited resources, is there really a path to being able to contribute to the kinds of research that would advance things in warehouse scale computing?
Yeah, that's a great question. I think it is true. It is harder these days. I think it's been harder for a while, and I think our field is unique for that. If you go back 20 years, VLSI and CPU design was at a time that, projects from major institutions funded by DARPA and NSF were able to build microprocessors that could compete with microprocessors from AMD and Intel and IBM, perhaps in some ways. And as industry matures, that becomes more expensive and more complicated for this to happen in academia. So just like in those cases, we have to be more creative in doing this. I think, on one hand, there's a lot that one can do today with the fact that public clouds exist. So to the extent that one actually has the ability to experiment with simulated hardware designs on public clouds certainly will help significantly. And there's still, I think, a place for scaled experiments and prototypes to tell us something about it. And I feel like, one of the things that I would love ISCA and other conferences not to do is to reject papers, for example, because they have been only done with scaled down experiments that were, those that were possible to be performed in an academic environment. I believe that carefully crafted scaled down experiments can teach us a lot as well. And then finally, I think that, all of these companies have different ways of having faculty come in and spend time on sabbaticals, which has been a way that we have been able to collaborate with academia as well. Of course, that doesn't scale quite as well, but it is a difficult topic for any discipline that matures, and that becomes very expensive to work on.
Thank you. David Wood asks, can you comment on how you see the future of accelerators in the data center?
Yeah, it's interesting, right? I see it sort of two ways. I mean, one way to see it is that the tricks we've been using so far for accelerating neural networks in particular are not the new Moore's law, right? This is not, there's no illusions of that. It's just that it's a field that's new enough that big leaps are still possible, but it's of that kind that these leaps are going to become smaller and smaller over time, just on that one trick we're playing. So in some ways, I think accelerators will remain incredibly important. The rate of improvements of neural network accelerators is expected to slow down, although they will continue to get better, I think, faster than general purpose computing. There is also, though, a huge amount of mind share in other kinds of accelerator designs. And I wouldn't rule out the possibility that, you know, another kind of accelerator could come out of all of the work that's been going on this area. Certainly accelerators for things such as compression and security have already been sort of very popular. But I expect that there will be other opportunities. I don't know that there will be another opportunity. I can't see one that's as big as the first big, you know, TPU class sort of designs. That was a huge, huge leap. But I wouldn't put it past the creativity of people in our field to do so.
Luiz Cese asks the next question. What are your thoughts on democratizing access to specialized hardware design and use?
Wow. You know, being a liberal South American, democratizing things in general is something that I am prone to be for. I guess I'll start by just taking the opportunity to tell Luiz and Karen how honored I am to be in the same award ceremony as the two of them. You know, congratulations. I do believe this is important, and I think that in a world where you know, Moore's law has really settled, in some ways it may level the playing field to allow others to execute on useful designs. Now, there is still a need to reduce the complexity and how laborious it is to design really high-end systems, silicon in general, and accelerators in particular. So to me, I think the main impediment is that the overall design flow for chips is still incredibly slow and incredibly onerous. And if anything, that is the one thing that needs to be optimized the most for those kinds of designs to be democratized.
Great. Janil Gandhi asks for you to comment, and I keep losing this. Give me a second. Can you comment on data centers, on how data centers would transform in the next 10 years with edge and fog computing gaining traction? What do you see as the new problems?
Yeah, I'm fascinated by this. You know, I don't see edge computing in the sense that when people refer to it as being the data center really will not be, you know, 1 million servers in a building, but it's going to be 1 billion cell phones everywhere in the world. I don't see that working personally. I feel like in particular, given the fact that there's no Moore's law for battery, these devices are still limited by the energy budget that they have. And increasingly, we need that energy budget to sense the world around you. We probably need to use every joule on these devices to do things that can only be done in situ, right? And that in and of itself, given the low energy budget that's available, probably will consume all of it. And I don't expect significant computation really to be running here, aside from, you know, specialized accelerators like we've had DSPs for the longest time in these systems, and TPU-like things certainly are arriving in that space. But they'll be rather specialized, I believe, to sensing the world around you. I think the interesting thing is whether there is a space for a middle tier, something that's in between, you know, a few gigantic data centers spread around a continent, and the edge devices that everybody has. Whether there is a role to play for edge Think of this as, the evolution of CDNs, of content distribution networks, where you begin to actually have some of those computations still on tethered devices in household facilities, but physically much more near the customer and the user. And I think that the division of labor and what can be offloaded from these kinds of devices to those kinds of middle tiers is a fascinating problem.
So I'm sure the next question will not surprise you. This is from Jose Martinez. How do you think quantum may or may not impact Google in your own work?
Oh, that's a really good question. Quantum computing, I think, is one of these things that we know is going to be very important. We know it's not going to be in the next 5 years. Beyond that, we have lots of confidence in different kinds of approaches, but very few of us have firm beliefs here. It's still very early days. So it's an area that I think will require continuing attention from this community. It's an area that will require continuing funding. I fear sometimes that society at large may see quantum computing in the way that AI was in the 70s, or to some extent VR has been for the last 5 years, in which there's a lot of hype and then it underdelivers, and then the investment in the area dries out for a long time. And I think that'll be a mistake. But in short, I don't see it having an impact on what we build for production at Google in the next few years. There's a few things we need to keep an eye on. Building quantum robust cryptography schemes is very, very important. We need to begin working on that right now. But besides that, I think that it's a long march. It's something that will require continuing focus for a good decade or so for us to be able to take advantage of that. And I am confident it will be important.
So I'll move on to a slightly different topic. Lizzie John asks, what is your advice to educators on what to focus on while educating the next generation of computer engineers and scientists?
Wow. I feel a little bit not in nearly as strong a position as you, Sanjay, and others in the panel to answer that question. I think the last time I taught a class was a graduate student class at Stanford quite a few years ago. If I look at the folks that arrive at Google, I think there are two things that I like to emphasize. One of them, being a good programmer is really important. Doesn't matter what you are, where you are in the field of computer science. Make sure you're graduating good programmers, whatever that means for you. Not being prolific, not speaking that language is an impediment, I think. So I tried very hard to become a programmer during my time at Google, and has been super important to me. The other thing that I think is important to recognize is a non-technical issue, is that unlike when I entered the field, the kinds of problems we solve today are at the degree of complexity and scale that a single superstar is much less likely to really move the needle. Really important things today are done by big groups. And I'm sure you see that at ISCA, the number of authors for papers, I think, has been creeping up over the years. In biology, it's happened a long time ago, papers with 40, 50 authors, right? Things become to be complicated. And what that means for the way we educate our students is that we need to educate students to think of themselves as a team and evaluate their performance, not as much by their individual prowess, but in what ways their addition will make the team better. And I see that every day at Google, where, the difference between a very good programmer and the ninja programmer in a very, very large group that needs to operate at a very high degree of performance in a very complex environment with tens or hundreds of people need to work on the same project. The difference between those two is not their ability to program or their technical prowess primarily. The difference between those two is how they work with their teams. So if you are able to have more team-based projects to sort of understand how to begin getting folks to practice that kind of teamwork, I think it's going to help them tremendously in their careers. It's a team sport.
Indeed. It is exactly 12 p.m. And so I think we do need to move on to the next session. And that next session is, so before we do that, thank you, Luiz. This was a truly inspiring talk.